Sure. Thank you. Thank you very much for the introduction, Balu. I'm sorry I'm not able to give more, uh, but I'm happy to join you today. So, what I'll speak about is maybe not so familiar to people in the audience. Please do ask questions. But as Balu said, I will try to connect that with things to do with the circle method, especially with the partition function and uh, properties of random partitions and related objects connected with partitions. And so the context for those investigations has to do with the representation theory of the symmetric group. So I'll try to explain the motivation and the problems. If you're not familiar with the character table, don't worry about it too much because I'll try to explain in number theoretic terms what the objects are, and you will see what it has to do with the structure of partitions. So the work that I have is joint work with a colleague of mine, Sarah Palouse. It began about 5, 6 years back uh, when we were investigating uh, congruences in the character table, and then we wrote a couple of papers on it, and most recently we thought about actual zeros in the character table as well. So the object of interest is the symmetric group Sn, which is a big group with n factorial elements. And the main object is the representation theory of this group. So it has a certain number of irreducible representations or characters attached to these irreducible representations. And the number of these irreducible representations is a familiar function in number theory. It's the number of partitions of n. The number of partitions of n is also the same as the number of conjugacy classes in Sn because uh, every cycle gives you a conjugacy class, and then the conjugacy classes are just given by cycle decompositions of permutations. And the lengths of the cycle decompositions uh, determine a conjugacy class, and that's the same as a partition. Now, many things are known about the partitions. One of the first The genesis of the circle method is this famous result of Hardy and Ramanujan, and I'll try to explain this result, that there's an asymptotic for the number of partitions, which grows like this. It grows like exponential of some constant times square root of n. The constant is quite pretty, 2 pi over square root of 6, and then there's a little 4n root 3 in the denominator. So you have two ways in which partitions occur. One in giving you a conjugacy class of the group, and another as giving you a representation of the group, an irreducible representation of the group. So I'm going to let lambda denote a partition corresponding to an irreducible representation, and mu is a partition corresponding to a conjugacy class. And the character table is a square table of Pn by Pn square table, and it has these character values. So uh, each uh, each irreducible character corresponding to lambda, you evaluate at a conjugacy class, and you get an integer out of this. And this is the number chi lambda mu that we are interested in studying here. So this is something that you could do for any group. It's a special property of the symmetric group that you get exactly integers in this case. And the theory has been studied for a long time. But very recently, only about maybe 10 years back, there was a mathematician, Alex Miller, who made numerical investigations of this character table. Now, the table grows very rapidly. Even when n is 76, you can see that there are about 9 million partitions. So if you're going to look at a 9 million by 9 million table, it's a difficult thing to compute with this. But what he observed was that if you look at the character values, he found that about 87% of them are even. For slightly smaller values like n is 38, there are only 26,000 partitions. You can compute more, and he found that a good proportion are even. You can see that the proportion for 76 that are even is a little bit larger than the proportion for 38. A good number of them are multiples of 4. About 2/3 of them are multiples of 3. about half of them are multiples of 9, half of them are multiples of 5, and so on. And he also found that about a third of them are 0. So this data, you can see, is not so suggestive, but he made a bold conjecture. He conjectured that if you look at the proportion of even elements in the character table, uh, the proportion tends to 1 as n tends to infinity. So almost all the entries in the character table are even. And then he conjectured that, in fact, it's true not just for the prime 2, but for every prime p, that the proportion of things that are multiples of p tends to 1 as n tends to infinity. He actually conjectured the same thing that holds for uh, multiples of any prime power as well. So for 3 squared, 5 squared, and so on. Again, all these proportions, he said, he conjectured 10 to 1. So he proved an interesting result himself, that if you take an irreducible representation at random, lambda is chosen at random, and now you choose an element of the group at random. So instead of taking P of n conjugacy classes, the character value at an element is the same as the value for every element in its conjugacy class. So, but if you sample all the elements of the symmetric group rather than just the conjugacy classes, he could prove that those values tend to be 0 quite often. And I'll try to explain that there's a familiar problem in analytic number theory, which this is related to, which has to do with smooth numbers. And that's kind of behind this particular version of the result. It has to do with the fact uh, that there are lots of n cycles. The number of n cycles in the symmetric group is like n minus 1 factorial. So if you pick an element of the group at random, it's likely to have large cycles. Just as if you pick a number at random, a number n up to x at random, it's likely to have a large prime factor. And there's kind of a strong analogy between the cycle decomposition of permutations and the partition and the factorizations of numbers into primes. Now, then there are other special situations in which people had studied this even much earlier. John Mackay had computed the dimensions of irreducible representation. So this is the character value evaluated at the identity permutation. And here he could compute exactly how many of them are odd. And the number of values of these that are even does 10 to 1. And McDonald did a similar calculation for the number of these that are multiples of any prime p. Then there were some partial results by a number of authors. These either could get some proportion of values being 0 mod p or 0 mod 2, or for certain particular kinds of irreducible representations or conjugacy classes, they could prove that the values were 0 mod p. Then about 6 years back, Palouse and I first proved that Miller's conjecture is true for all primes p. And in fact, we could do this with some uniformity. So you could take your prime to go up to like log n, essentially log n divided by log n squared. And most of the entries are going to be 0 mod p for every prime up to this range. So the story of this is that my co-author Palouse had proved this result, proved Miller's conjecture for 2, 3, 5, 7, 11, and 13. And then her proof broke down at 13. And then it kind of fascinated me how you could have a proof that works for all these small primes and then stops. And so I started thinking about it as well. And then we were able to prove it eventually for all primes p. And then a few years later, we were able to prove that the same result holds not just for primes, but also for all prime powers. You can take prime powers up to basically log n, and most of the values are going to be divisible by your prime power. I'll explain why it's a little bit harder to do prime powers than primes as the talk goes on. But the big open question that now remains is how many character values are 0? So one way in which you could imagine that most of the character values are multiples of p is simply if most of them were 0, then of course they're going to be multiples of p for every prime p. So the question is it also the case that the proportion of character values that are 0, maybe that also goes to 1, in which case it would explain why you have these divisibility properties. However, this doesn't seem to be the case. Miller and Scheinerman recently did more large-scale investigations in the character table, and this time they did Monte Carlo simulations going up to the size of the group being 200, or sometimes going with, for certain special classes of zeros, going up to 50,000. And what they find is that the proportion starts going down, but it goes down extremely slowly as n gets larger. And what we proved recently is that the proportion of zeros, so really I mean something more here, that all the general methods that we have of producing zeros in the character table, we can analyze the most general result that we have towards guaranteeing these zeros, and we can compute the asymptotic in that case, and it turns out to be a proportion of which goes to 0, but it goes to 0 slowly, like 2 over log n. And it may be that this is the right asymptotic, that the number of zeros in the character table tends to 0, but it tends to 0 very slowly, like a constant over log n, or 2 over log n. But this is wide open, and in fact, I don't even know a good way to show that a positive proportion of, I don't know any way to show that a positive proportion of entries in the character table are not 0. So it's still possible that almost all of them are 0. We just haven't been able to rule it out. So now let me try to tell you something about how these character values are computed. And one important way of calculating this is a recursive procedure, which is called the Murnaghan-Nakayama rule. And this will play a key part in motivating the analytic number theory questions that will next come up. So the way in which you can compute this character value, so each partition you can think of using its Young diagram or Ferrer's diagram. So you have a bunch of boxes like I have drawn here for lambda and mu, and so I've given you two of these examples of what a partition looks like. And what you're supposed to do is that you should take a part in mu, and you have a procedure of calculating the character value chi lambda of mu in terms of partitions that you get where you remove the one part from mu, like you remove maybe the largest part mu1, and correspondingly you remove from lambda certain hooks, or what are called rim hooks. Now, I don't know if I can point in this anymore. Let me see if this works. Yeah. So suppose I have this part of length 3. So this I remove from mu, and correspondingly I want to remove something from lambda, and what I want to remove are rim hooks, which are hooks like this. So that's a hook of length 3. If I remove it, if I just remove these 3 boxes, I'm still left with a partition. So border strip is something that hugs the border of this partition. And then if you remove something from the border, you're left still with a partition. So I have some choices. I could either remove this 3 or I could remove that 3. And those are 2 border strips of length 3 that I could remove, and I would get a new partition in place of lambda. Okay? And then the Murnaghan-Nakayama rule is a recursive way of computing the character value in terms of removing a part from mu and removing corresponding hooks, rim hooks from lambda. And the recursive procedure uses the character value of the new partitions multiplied by some signs. So this is always plus or minus 1, and the plus or minus 1 corresponds to how many rows there are in the hook that's being removed. So in this case, there are 2 rows, and then the sign is going to be minus 1 because it's the number of rows minus 1, so which is 1, and then minus 1 to the 1, which gives you minus 1. So this is a combinatorial way in which you can compute this character value. And this tells you that there are certain things that you can have uh, which will guarantee that the character value is 0. So for instance, suppose you had a partition where one of the parts mu is, there is no hook which is of the same length as the size of that part, then you're not going to be able to use this procedure. There will be a part of mu of a certain size, but you won't be able to remove a corresponding hook, a rim hook of that same size from lambda. So that's what I want to make a little bit more transparent here. So the rim hooks I can keep track of by writing down something called a hook length. The hook length of this box is that rim hook. The hook length of this box is that. I'm adding these 3 plus those 3. Okay, so I have those boxes, 2 plus 3 plus 1, 6. And the reason I want to think of the 6 is that that 6 corresponds to a rim hook, which looks like that, which has the same length, as you can see. Okay, so the way I've marked these hook lengths, the possible lengths of the border strips or the rim hooks that I can remove are captured by the hook lengths that I've written down here. So if I don't have a hook length of some size, then there's no way to remove a border strip of that same size. And a partition is called a T-core if there's no hook length of size T. Now, there's a combinatorial fact which is not easy to see unless you think about it just right, which is that a partition that has no hook length of size T also has no hook length of size any multiple of T. Okay, I think in the diagram that I have drawn, you should be able to see it. If it doesn't have a hook length of size, well, what can I see here? And 10, maybe 11. It's also not going to have any hook length of size, a multiple of 11. But here there's nothing that's larger than 10 anyway, so you can see that transparently. Okay, so to summarize, if I have a partition lambda which has no hook of size T or no hook of size a multiple of T, and the partition mu has a part of size T, then I cannot, when I try to use the Murnaghan-Nakayama recursive procedure, taking this part in mu of size T, I'm not going to be able to get started because there's no border strip that I can remove from lambda, and therefore the character value is forced to be 0 in this case. So this is one of the main things that we're going to use to try to understand both when the character value could be 0 mod p and also when it can be 0. And this is the key fact that you have to keep in mind about what these character values look like. I'll tell you one more fact about this, which also has some number theory built into it. Now, some of these objects have been studied for a long time. So for instance, if you look at the number of T-core partitions of M, so these are partitions where there are no hook lengths that are multiples of T, there's a theory of this that, because of the connection with representation theory, people had studied it for a while. There's an old result of Granville and Ono, which says that there are always T-cores for every N of a certain size. As T gets larger and larger for a fixed N, you can imagine that more and more things will become T-cores because you're not likely to have a part that's divisible by T as T gets larger and larger, a hook length that's divisible by T. So it has a nice generating function which differs from the usual generating function for the partition in this numerator. If you want to think about it in terms of number theory, this is also a modular form because what I have here is an eta function, and then this is some big power of an eta function evaluated at tz, and then you can see that it'll be a modular form of some weight like t minus 1 over 2. Now, if I want to think of trying to get character values that are 0 or 0 mod p, I would like to find partitions mu where maybe there's a partition mu has a large part of size t, and I would like to understand how often a partition mu contains a part of a certain size. And if this part is very big, I might expect that a partition lambda is likely to be a t-core, and I would like to understand how likely it is that a partition lambda is a t-core. So I'm led to statistical properties of what a random partition looks like. How big is the biggest part of a random partition? What do the hook lengths of a random partition look like? And if I can understand these statistical questions, then I can go back and say something about the character table of the symmetric group. So now let me go back to talking about this classical object, the number of partitions of n, and try to now say something about the circle method, which is the origin of finding asymptotics for this. And there are more ways in which you can do this, but I want to just give you a quick way of thinking about it in terms of the saddle point method, which gives you an easy way of computing these asymptotics. And this technique is very useful in all over the place in analytic number theory, and I'll try to give you one or two more examples where it can be used. Okay. So the generating function for partitions, as we've seen, is this product of 1 minus z to the n inverse. And then you can recover the number of partitions of n by the Cauchy integral formula, which if I reparameterize the circle in terms of polar coordinates, I can write it as that integral. Now, you could do this for any value of q that's less than 1. And the great advantage, the great power of this method of the saddle point method or the method of stationary phase is that you can choose this parameter q in a careful way. Okay. Now, one way in which you can think of how to choose the value of q is something which, again, is a very powerful technique in analytic number theory called, sometimes called Rankin-Strick. In this case, Rankin-Strick simply says that I have this generating function Pn z to the q to the n. All its terms are positive if q is a positive number. And I can bound one of these terms Pn q to the n by the full generating function f of q. So therefore, the value Pn is bounded by f of q over q to the n. Another way in which you can see it is that if you look in this integral formula, this is of size 1. And if you take absolute values here of this generating function, the coefficients of this power series are all positive. So the function is going to be bounded in size by just the function at z equals q. So once again, you get the same inequality. Now you have this inequality that's valid for every value of q between 0 and 1. And the best inequality that you can get is by choosing the value of q so that this is minimized. Now it's easy to figure out how to choose it so that it's minimized. I can take derivatives of this. I want to take the derivative of this and set it equal to 0. And it's easy if I take logarithmic derivatives. So if I take the log of this and differentiate that, then I get q times f primed over f of q is the same as n. So that gives me an implicit relation which tells you what Q should be in terms of n. And then that value of Q is what I'm going to use in the Cauchy integral formula and try to evaluate the integral. Now, there is another feature of this which is important to note. I took this function and optimized it in Q so that I get a minimum value in Q as I vary Q between 0 and 1. Now, if you think of what the Cauchy-Riemann equations are going to tell you in this context, the function takes a minimum as Q ranges, the real part varies. But if you think of what happens as the angle varies for that value of Q, it's going to take a maximum there. So in other words, you're going to get a saddle point. As you vary the real parameter Q, you're going to get a local minimum. And as you vary theta, you'll get a maximum at theta equal to 0. Okay, so that's why it's called the saddle point method. The point that you get is a saddle point for this function. So let me give you a few more details on this. So if I take the log of this generating function, I can understand how that behaves. I use the Taylor expansion for log, collect terms of the same size. So I have here sigma of m is the sum of the divisors of m. And then the relation that I wrote down is that if I take the logarithmic derivative here and then set that equal to n after multiplying by q, the relation that I have is that, so the m's will cancel out. So I have sigma m q to the m is n. So that's the implicit relation connecting q and n. Now you can do a simple calculation in analytic number theory of evaluating, if I do sigma m e to the minus m over x, so you can write down the Mellin transform of that. It's the generating function sigma m over m to the s multiplied by gamma of s x to the s ds, integrated somewhere in the range of absolute convergence. You shift contours and compute the residue of the pole in the standard way, and you will get a contribution here. This pi squared over 6 is a zeta of 2, pi squared over 6 times x squared, and then there's an error term of size x. You can be a lot more precise, but this is just to write something down. So basically, I want to choose this q. Maybe I choose q to be e to the minus 1 over x, and then I want pi squared time over 6 times x squared to be the same as that n. So that tells you what q is. Q is given by this fundamental relation. You can compute it more precisely. So if you look in the Hardy-Ramanujan papers, there will be a more refined formula analyzing this much more carefully. But this is good enough for our purposes at the moment. Now, if you choose this value of q, then you can also plug into this formula this value of q, and then try to compute what the asymptotic looks like. So here, another small computation allows you to compute asymptotics for not just sigma of m e to the minus m over x, but you can use the same standard technique to work with sigma m over m e to the minus m over x. Here, you should work out some second order terms as well. And a lot more can be said here. You don't even get an error term of big O of 1 over x. You can arrange it so that you get an exponentially small error term. And this has to do with the fact that this object, being the logarithm of the eta function, is essentially a modular object. So there's a modularity relation that it satisfies, which you can exploit to get much, much more precise asymptotic formulas here. But this is enough for us. So if you plug it in, you can see that f of q or log f of q has this asymptotic formula. And if you look at f of q over q to the n, it has an asymptotic formula of this type, where there's some constant here, which you can just write down from this formula. Okay. Now, what I've shown so far is that the number of partitions of n is bounded by this, because we chose q so that this object was minimized, and that gave you a bound for the answer. And so that's the upper bound. for the number of partitions. It's already a very good upper bound, as you can see, because the asymptotic formula of Hardy and Ramanujan has the same nature here. And the main difference is that instead of an n to the 1/4 in the denominator, you get an n in the denominator. So let me quickly say why you get an extra n to the 3/4 in the denominator coming in this asymptotic formula. And this has to do by looking at in the Cauchy integral formula, I don't just have f of e to the I theta, just of f of q. I have f of q e to the I theta. And I can try to understand how f of q e to the I theta behaves as theta varies. So if I compute using the function for the log, you can see that this sigma of m times q to the m, that was the f of q. And then this cosine m theta, that's going to give you the size of f of q at e to the I theta. So you can see that this 1 minus cosine m theta, it's always going to be some positive number because cosine is always between -1 and 1. But if the cosine varies around at all, it doesn't always stick towards 1. If theta is 0, it's always going to be 1, and I don't get anything here. But as soon as theta moves away from 0, sometimes this is going to be positive, and I'm going to build a large negative contribution here, which means that this function is decreasing rapidly as theta gets larger and larger. So one way in which you can see this is that, if theta is big, you can use this simple formula. I can just compute using the geometric series, and I can show that this is substantially big, so that this object has decreased very rapidly from its value at theta equal to 0. Or I just have to worry about what happens when theta is small. And when theta is small, I can just use a Taylor expansion. This 1 minus cosine m theta, I can replace it by m squared theta squared over 2. And then I can compute what this object is. And I get a term which looks like theta squared times n to the 3/2. You see, you have a sigma m, which is roughly of size m. And then there's an m squared, which cancels with 1 m squared. So this whole thing is of size roughly m squared. And I'm going to sum over m going up to square root of n, because q is like e to the minus constant over square root of n. So m goes up to square root of n, and then I have a sum of like m squared here, so I get an m cubed. So that's the n to the 3/2 that I get here. Okay, so this basically means that the values of theta that are important are in the range of n to the minus 3/4. And so if you compute that integral, you get a Gaussian integral on the scale of n to the minus 3/4, and that gets multiplied to this 1 over n to the 1/4, and that's where you get this Hardy-Ramanujan asymptotic with an n in the denominator. So since this is maybe the main part of the talk, which is going to deal with the circle method, maybe I should stop here and see if people have any questions on anything so far, or if there's some part of this calculation that you might like more details on. I don't know if it's easy for people to ask questions.
Hello. Yeah, I think we can perhaps, anybody wants to ask something?
Yes, sir, you can continue.
Okay. Okay. All right. So then let me give you a couple of other situations where this method of using the method of stationary phase is extremely useful, and give you an exercise as well in this context. So in analytic number theory, a very important object is the number of smooth numbers. So these are integers up to x, all of whose prime factors are smaller than y. We want to think of y as being some power of x, maybe like x to the 1 over 100, and you want to compute how many such integers there are. And a very nice way to do this analytically is to set this up using Perron's formula. You can write the generating function for integers, all of whose prime factors are smaller than y. That's this, it's the same function as the zeta function, except that instead of having the full Euler product, I only take the Euler product over the primes up to y. And then I can use the Mellin transform to Perron's formula to understand the sum of numbers up to x, all of whose prime factors are up to y. And now, once again, if you want to get an understanding of this, the key is to choose the line of integration carefully. And again, Rankin-Strick kind of tells you how to choose this line. You want to choose the line of integration so that this integrand as a function of c is minimized. So you want to minimize this object, zeta of cy x to the c. And once again, you can do this by taking logarithmic derivatives. You get a sum over primes, which has to equal log x. It tells you how to choose c. And then once you choose c this way, this function will have a saddle point once again. As a function of the real part, it takes a minimum value at this point c. And as a function of the imaginary part, it takes a maximum value at t equals 0. And then you can compute this integral by the method of stationary phase, and you can get an asymptotic for the number of smooth numbers up to x, which is valid in a very, very uniform range for y. And this was first carried out by Hildebrand and Tenenbaum in the 80s, and the method is an extremely useful one in number theory. Let me give you one more exercise, which is kind of fun. It was actually an old Erdős problem, but if you think of it using the saddle point method, you might be able to see quickly how to solve this problem. It's a good exercise in trying to set this up as a nice problem using generating function. The problem is a simple combinatorics problem. Take all subsets of 1 to n and take subsets where if you add the reciprocals of these numbers, you get an answer which is less than or equal to 1. And the question is, how many subsets are there? Are there fewer than 2 to the n subsets of this, which is a maximum number of subsets? What proportion of subsets can you find? So one way in which you can get such a subset is to take all numbers between n over e and m. And then if you add all the numbers from the reciprocals of the numbers from n over e to m, you get 1 asymptotically. So any subset of that interval will satisfy this property. What is the best that you can do? And can you actually compute an asymptotic for the number of such subsets? So I leave that to you as an exercise. Okay. So now let me return to the character table again and try to say something about how this kind of calculation can help you think about when character values are multiples of something, multiples of a prime, or when they are 0. Now, let me first start with t-cores. So the generating function for t-cores is the same as the generating function for partitions, but then it gets multiplied in the numerator by this object. So if you think of trying to understand how many t-cores there are, you could write down the same kind of contour integral, the same integral here, multiplying by this factor. And we can try to evaluate it on the same circle that we had before. So take the same value of q and try to evaluate on that circle with radius q. So if I try to do that, the main difference is going to be this factor. And if this factor is close to 1, then I can imagine that in this formula, it's not changing the asymptotic from what the asymptotic for the number of partitions, and most partitions are going to be t-cores. Okay, so the question is, if I take this value for q, how large must t be so that this answer is close to 1? So you can see that as t gets larger and larger, q is some number which is less than 1, if t gets larger and larger, this is going to get exponentially small. So the answer is going to go to 1. And then if I take something to the power t as well, that's still going to be close to 1. So if t is very large, this is going to be close to 1. And the question is how large? Well, roughly speaking, if this is close to 0, I want this to be close to 0. If it is close to 0, then it's going to be the only value that's going to be that matters is n equals 1. For n equals 2 and 3 and so on, it's going to be even closer to 0. So the question is, this is close to e to the minus q to the t. And then the question is, when is t times q to the t small? If that is small, then I get the exponential of something like e to the minus t times q to the t. And that's going to be close to 1. So the question is, when is that going to be small? Well, t is this number e to the minus constant over square root of n. So t should be at least on the scale of square root of n. Otherwise, I'm not going to get something close to 0, right? This guy will be pretty big. Well, if t is like square root of n, well, this t is like a square root of n. And that if t is just of size square root of n, that'll be a constant. This will be of size square root of n. So that's not going to be enough. So I need some more help from this q to the t. So this square root of n gets rid of that square root of n. And now this log is going to make the q to the t to be like 1 over square root of n. So the 1 over square root of n will now cancel with the square root of n. But now I've introduced this log. So this will become square root of n times log of square root of n. So now I need to put and add an extra log, so that now when I take q to this log, I get another extra log factor which cancels this. Okay, so now I'm okay. If I choose it on this scale, then the exponential of this is going to cancel that. The exponential of this is going to cancel that. And now I get something here, an e to the minus x. So long as that e to the minus x goes to, that x goes to infinity, I'll get this tq to the t to be small. So this calculation tells you that if mu has if you have a partition mu whose largest part is bigger than this number, then the partition lambda is going to be a t-core, and then I'm not going to be able to remove a rim hook of size t from the partition lambda because it doesn't have any strips of size t, border strips of size t, and then the value of the value is going to be 0 on this. So in other words, if mu has a very large part, the part is so large that almost every partition lambda is going to be a t-core, then the character value is guaranteed to be 0. Okay. Now, this is the calculation that Miller first used. If you pick an element G from the symmetric group at random and then take an irreducible representation lambda at random. And the reason for it is that if you pick a random element of the symmetric group, you can take a random element of the symmetric group and write down its cycle decomposition. And this is actually going to look almost exactly like the prime factorization of a random integer. And if you go back to this other problem that I discussed of smooth numbers, it turns out that there is a positive proportion of integers that will have a prime factor that's larger than n to the 1 over 100. Okay, so it's a very small proportion. It's like 1 over 100 factorial, but still it's a positive proportion of numbers will have a prime factor larger than a very large proportion of numbers will have a prime factor larger than n over 100. So, and similarly, a large proportion of the elements of the symmetric group will have a cycle of length which is larger than n over 100. And so those partitions will have a largest part much larger than this. It'll be of size n over 100 rather than just square root of n times log n. And therefore, this character value will be 0 for most elements of the group. but that's not the same problem as asking for conjugacy classes. So another way to say it is that if you think of the conjugacy class that just consists of an n cycle, that's just one element as you range over all partitions mu. But on the other hand, as you range over all elements of the group, that's like 1 over n of the elements of the group. There are n minus 1 factorial n cycles. So this is a different result from what we would like. And we have to understand what happens if you take a random partition and you want to look at the largest part of a random partition. And the structure of random partitions also has been studied for a long time. And there are results of Erdős and Lehner going back a long ways, maybe to the 50s, where they showed that the largest part of a random partition is very close to the threshold that we looked at before. It's like square root of 6n over pi, same constant, log of square root of 6n over pi, but there's no log term here, but instead there's just a constant term here. Okay? So it is barely smaller than the threshold that I need to ensure that most partitions are T-cores. So at this stage, most partitions are still not T-cores, and only a proportion of like 1 over log n of them are T-cores. So this idea already will allow you to show that the number of character values is a proportion, some 2 over log n. You can get rid of this e with a little bit of extra work by just taking partitions mu with a large part, and then and then showing that if the part is if this v is at least as large as log, you know that lambda is going to be a T-core, but the proportion of that is only like a 1 over log n in this case. Okay. So in other words, this is the proportion that you get if you take the largest part of your partition mu, try to remove it from using a border strip of that length from a partition lambda, and this will succeed 2 over log n proportion of the time, but not a positive proportion of the time. Okay. To study congruences, there is one other nice trick which allows you to do more than just this proportion and allows us to get the proportion 1. And this has to do with another property of these characters, namely, you can compute the character values by another formula, and this is a formula which goes back to Frobenius. So you can compute the character value chi lambda of mu as the coefficient of some multinomial. So I have variables x1 to xn, and I write my partition lambda as lambda 1 to lambda n, but some of the last few lambda n's may be 0 because I can't really have n parts unless all the parts are going to be 1. And then I compute this exponent, this power of x1 to xn in a certain polynomial. And this polynomial is a complicated polynomial. One part of it is the Vandermonde determinant, that part. And then the other part are power sums of these variables x1 to xn, and the power sums are defined for the parts corresponding to my partition mu. So again, mu1 to mu(n), I write my partition mu as mu1 to mu(n), it may be in descending order, and then I'm going to set some of the last variables to be 0 if I run out of parts. Okay, so this is some complicated formula, but in principle you could compute it involving just polynomials and computing the coefficient of some polynomial. Okay, now how is this useful for congruences? The key is this lemma that if I take a partition of n and I look in this partition And whenever I see p parts of the same size in mu, I replace these p parts of the same size with one part of size pm. So I'm going to combine p parts of size m to one part of size pm. And I do this as many times as I want. And what I claim is that there's going to be a congruence if I combine p parts of one size to one part of larger size, then the character values are congruent modulo p. And the reason for that is that in Frobenius's formula, the only way in which something changes is in these power sum calculation. On one side, I would have the sum of x1 to xn, the power sum at m raised to the power p. On the other side, I would have the power sum at mp, but these two objects are this congruent modulo p. And so if I now unwind what Frobenius's formula tells me, I get a congruence of these character values. So this is a nice trick because what it allows me to do is that if I start with the partition mu, I keep applying this and I arrive at a new partition mu tilde where no part can appear more than p or more times. Because if a part appears more than p times or more, I could have combined all those p parts into one part of a larger size. And if I do that, I get a congruence between mu and mu tilde at modulo p. Now, this mu tilde is likely to have a large part because what I've done is I've taken a bunch of parts in mu and combined them into getting bigger and bigger parts. Now, if it has a part which is larger than the threshold for t-cores that we looked at, then I would know that this value is likely to be 0. But if this value is 0 on the nose, then that value is going to be 0 modulo p. And so even though I may not be able to show that this value is 0, I can get a congruence to something which might be 0, and therefore I can get divisibility by p. And that's basically the first result that we had, is that this procedure of starting with a random partition mu and accumulating partitions of this and parts of the same size to getting progressively bigger and bigger parts, it is going to lead to a partition. Typically, I'm going to end up with a partition mu tilde, which is in fact a proportion larger than the size, the usual size of the largest part in mu. And I only wanted to beat this size by a factor of log log. So if p goes up to only log n over log log n, I'm going to beat it by a considerable amount here and then get the main result that I want. Okay. So this is the main result that we had for divisibility by primes p. And the heuristic explanation for that is that if I look at partitions of n, where each part appears no more than k minus 1 times, I can work out its generating function. And now here is another exercise for you, is that you can try to compute what the asymptotics for this number of partitions is going to be. You can use the method of the saddle point method for this object. You can compute exactly what the answer is going to be. You can work out asymptotics, the analog of the Hardy-Ramanujan asymptotics. The radius that you're going to integrate on is going to be something a little bit smaller. And now if you compute the analog of the Erdős-Lehner result, you will find that the largest part of such a partition where you constrain no part to appear more than k times, you can see that if all the parts are constrained to be not to appear too many times, then the largest part is forced to be large, a little bit larger than in a random partition. Okay, so that's the heuristic explanation for why when you carry out this procedure, you're going to get typically a partition mu tilde, which has a largest part, which is larger than just the partition lambda that you started out with. And the reason this is not a rigorous argument is that what you're doing is you're sampling a random partition of n. You're writing down this procedure to get a new partition mu tilde. but this may not be the same as sampling a random partition with no part appearing p times or more. It may not be the same probability measure on this space, and you have to be careful about making sure that that these two measures are not too far off. And they're actually a little bit off in a subtle way, but the basic feature doesn't change, and the heuristic that I gave you is still a good predictor for what happens. So that's like a rough argument for why the result on divisibility by primes p works out. And let me say a little bit about how divisibility by prime powers and then the zeros rather than just 0 mod p or 0 mod prime powers works. Okay. So for prime power divisibility, the argument is more complicated. And the reason for that is that the argument for primes use the fact that if you take a polynomial and you raise it to the power p, then you get a congruence modulo p. If you take f of x1 to xk and you raise it to the p, that's the same as f of x1 to the p up to xk to the p modulo p. But if you take higher prime powers, it's no longer the case that I can just replace this by prime powers here modulo p to the r. Instead, what you have is a funny kind of congruence. You can take 1 power of p and put it inside x1 to the p up to xk to the p, but then you must raise it to the power p to the r minus 1, modulo p to the r. That's the congruence that you get. So for r equals 1, this is the congruence that we are all familiar with, the Frobenius congruence. But then for r larger than 1, you don't get full information out of writing down this congruence mod p squared, p cubed, and so on. So in other words, what you're allowed to do is that you can take p to the r parts of a given size p, and you can combine them into a part of size pm, and then you get p to the r minus 1 parts of size pm. But if you use this procedure, you don't end up with a value with the largest part in mu, which is large enough to ensure that there are t-cores, and the argument doesn't work as stated. And instead, you get a much more complicated combinatorial argument that you have to work out, where this plays a key role, but the argument is not as simple as the argument for primes. Okay. So now let me get back to zeros in the character table. So the main argument that I gave you before was that if I have a partition mu, and if I write them in descending order, so mu1 is the largest part of mu. If I don't have a way of removing a border strip of length mu1 from lambda, then I know that the character value is 0. This is the argument that we were using before. And these zeros are called by Miller and Scheinerman zeros of type 1. More generally, if you take any part in mu, and if you're not able to find a border strip of that length in lambda, then the character value again is going to be 0 by this Murnaghan-Nakayama rule. And these are called zeros of type 2. So these are slightly better, more general than the zeros of type 1. And then there's a still more general criterion that you can write down, which is due to Richard Stanley. And Stanley's criterion is that you can look at in your partition lambda, you look at all the hooks that are multiples of t. So if it's a t-core, then the number of hooks that are equal to t, which is the same as the number of multiples that are equal to multiples of t, they will both be equal to 0. So in that case of t-cores, they would both be 0. And Stanley's criterion is that on the one hand, you compute the number of hooks that are multiples of t in lambda. And on the other hand, in mu, you look at all the parts that are multiples of t, and you add all the parts that are multiples of t, and you divide that answer by t. Okay, so t times this p sub t is the sum of all the partitions of all the parts that are multiples of t. If the number of, if this quantity in mu is larger than the number of hooks that are multiples of t in lambda, then the character value can be guaranteed to be 0. So one way in which this can happen is that if the mu contains a part of size t, then this will be at least 1. And if lambda contains no hook length of size t, then that will be 0. And then that's the earlier cases that we have, that if mu has a part of size t and lambda is a t-core, then the answer is 0. But this generalizes that construction in a considerable way. And these are zeros of type 3. And this is the most general criterion that we are familiar with, in which guarantees that you have zeros in the character table. And it would be great if somebody knew other criteria for giving zeros, and then we can try to see what the asymptotics of those criteria would be. And the main result that we prove is that all these different criteria for finding zeros have the same asymptotic behavior, and they're of size the number of partitions squared times 2 over log n. So in fact, the number of partitions of type 3 that are not partitions of type pairs that are not of type 2, the number of those zeros is very small. It's off by like a power of n. But on the other hand, the number of zeros of type 2 that are not number of zeros of type 1, that probably has an asymptotic expansion with a secondary term of size log n squared rather than 1 over log n. But I don't know how to compute the asymptotic of this type. Okay. Another variant of Stanley's criterion is that if you write down these polynomials, so this is a product over all parts mu j in my partition mu. If this guy does not divide the product over all boxes, so these are, you write down the partition lambda in terms of its Young diagram, in terms of its boxes, and U is a box in this Young diagram, and then H of U is the hook length corresponding to that box. So you form that product that must be divisible by this polynomial, and if that divisibility doesn't happen, then the character value is guaranteed to be 0. Okay, this is slightly weaker than the condition that I gave here. This is still the most general condition that I know. Okay, so let me very briefly say what goes into the proof of computing that asymptotic. And again, there are lots of beautiful formulas in this area. And then to understand how this asymptotic works, you would have to use some version of an analog of Rankin's method, or this method of the saddle point method, the circle method in this context. So if you want to understand hook length, there is a beautiful formula of Hahn which allows you to compute this. So it's a 2-variable generating function. So on the one hand, I have a sum over all n and a sum over all partitions of n. And then z to the n is keeping track of all the partitions of the size n. And then I have a new variable y. And then I have, for each partition lambda, I'm going to compute y to the number of hooks that are multiples of t. And if you take that 2-variable generating function, it has a nice product representation. This part is just keeping track of all the partitions of n. And then this part is what we already saw when you're looking at t-cores. So if you put if you take y is 0, then the only term that survives here is when there are no partitions, if there are no hook lengths of size t or a multiple of t. So in other words, you're summing t-cores, and then that would be the generating function of t-cores. And then this generalizes the classical formula for the generating function of t-cores. And this formula, amazingly, was first, had its genesis in the physics literature, or a collaboration between a physicist Nekrasov and Okunkov, who are studying representation theory. So there was something called the Nekrasov-Okunkov formula, which is quite amazing. It's the same formula that goes back to Euler for computing partitions. If z is 0, this is just the generating function for partitions that Euler found. But amazingly, you have a generalization of this where you can put in any complex number z that you want, and it has a combinatorial interpretation in terms of all the partitions of n, and then you get to sum over all, you get to take this product over all hooks in your Young diagram for lambda, and then you take, for each of these hooks, you form this product of 1 minus z over h squared. H is the number of hooks in that, is the hook in that box, hook length corresponding to that box. So it's quite an amazing formula. So if you put z equals 0 here, the product will just be 1, and then that's just the usual product formula for counting partitions of n. So then there was a mathematician, Hahn, who generalized this Nekrasov-Okunkov formula and found many more combinatorial formulas connected to this. So his general formula, he sums over hook lengths that are going to be multiples of t. So that's what this ht of lambda is. Not all the possible boxes, but only the boxes that are multiples of t. And then you have a generalization of this. You can replace this 1 by a y, and then put in another factor t here. And then you have a formula for this in terms of products of suitable eta functions. So this formula, if you take z equal to 0, will give you the formula that I wrote down here, that formula of Hahn. So if you take z equals 0, that goes away and gives you exactly what I have here on the right-hand side. And here, what I have is y to the number of boxes that have a hook length that's a multiple of t. So now if you have this two-variable zeta function, you can now carry out analysis to try to understand how often the number of hook lengths are going to be multiples of t. So in Stanley's criterion, you're interested in figuring out how many times you can have a partition mu where the sum of the parts that are multiples of t is going to be larger than the number of hook lengths that are going to be multiples of t. So you'd like to understand how often you have partitions lambda where there's a small number of hook lengths of size t and a large number of, and partitions mu where there's a large value of the sum of parts that are multiples of t. And so if you want to study partitions where the number of hook lengths is small, again, we can play games with the analog of Rankin-Strick in this context, or the circle method in this context. You can take if you study the two-variable generating function, you can bound the number of partitions lambda with ht being smaller than k by y to the minus k times y to the ht here. If ht is smaller than k, this answer will be bigger than 1. So this is an upper bound for the total number of such partitions. But if ht is bigger than k, it's still some positive number, so that you're going to still get an upper bound. And that in turn is bounded by an upper bound where with a q to the minus n and summing over all partitions of n and letting n vary from 0 to infinity as well. And by Hahn's formula, I know what this object is, and I can write down an expansion for this. So now you can try to understand this by choosing q and y appropriately. I should choose q in the same way. If I want to pick random partitions, I will choose q to be in the same way in which we chose in the Hardy-Ramanujan formula to minimize this. So that's this e to the minus pi over square root of 6n that we've been looking at all this time. And then I would choose y in order to minimize this object times y to the minus k, I would choose y optimally for that. So this is some kind of calculus computation that you can carry out. And what you find is that we should really expect the number of hook lengths that are multiples of t to be roughly like n over t. Because if you write down the Young diagram for lambda, there will be n boxes because a partition of n will have n boxes in it. And then you might expect that if you're putting in the hook length in each box, you might expect that 1 over t of these boxes will have hook lengths that are multiples of t. On the other hand, if you want to compute the number of partitions mu, where if you add all the partitions that are multiples of t, that guy is large, then you can understand what that looks like combinatorially, because you isolate in your partition of mu. Let's just isolate the partitions, the parts that are multiples of t from the parts that are not multiples of t. So if I take at of n is going to be the number of partitions of a number into parts that are not divisible by t, then the partitions where the parts that are multiples of t sum up to L. Okay, so that's going to give you L times t. Then the number of those is going to be, well, I can take these guys and partition them in any ways that I like. And then the remaining parts, n minus TL, I want to partition them into parts that are all not multiples of t, and that's this function at of n. And this is no more than p of L times p of n minus TL. So if I want this pt of mu to be large, the number of such partitions will be, this L is going to be larger than k, and then I can bound it by p of L times p of n minus TL. And you can see that this L cannot be big because here I have an n minus TL, so this gets very small. But here, instead of a p of t times L, which is what you might expect, I have lost this factor of t. So this is likely to be pretty small. So it's unlikely to have my L to be larger than, say, 0.9 times n over t, whereas in the previous argument, I might have expected this ht of lambda to be like n over t. So this kind of heuristically tells you that at least for small values of t, it's very unlikely that Stanley's criterion is going to hold for small values of t, and you should only focus on the large values of t, which might appear at most once in mu, and then you're thinking of a partition where mu has a certain large part, and then that part needs to be a t-core, and this is the previous calculation that I was describing. What is the chance that you have a large part in mu, and what's the chance that lambda has a t-core for that part? And that gives you, and that is optimized for the largest part of mu1, and having lambda be a mu1 core, and that gives you a proportion of like 2 over log n. So this is some kind of rough idea of how we could evaluate the number of partitions that you get in Stanley's criterion and show that for all the different ways that we have of computing zeros, we don't get the proportion going to 1, it goes to 0, but we can quantify the rate at which it goes to 0, and it's something like 2 over log n. Okay, so that's everything that I know on this, on the topic of zeros, computing zeros and computing modular zeros in this character table. Thank you very much.
Yeah, it's okay. Any questions? Reports? Yeah. Okay, so thank you so much for the very nice talk. I had a quick question. In the final part, you mentioned the 3 criterias. So I was wondering if there are any converse observations?
No, not that I know of. These are only sufficient conditions that I know for finding zeros, but it could be that there are, extraneous zeros as well. So in other words, what you could do if we want to understand numerically, we could just take the most general criterion that we know, Stanley's criterion, remove zeros that you get that are accounted for this, take only the ones that are left over, and maybe you can see that that tends to zero faster than what has been accounted for, in which case then you would have some credence to the belief that you've accounted for most of the zeros.
Okay, thank you, sir.
Numerically, that seems to be kind of true, but it's not so easy to do numerics conclusively here.
Good, that thing, let me conclude.
Sorry, I didn't hear you fully.
Now it comes. Can you hear me?
Yeah. Mm-hmm.
Okay, therefore let me conclude the first session with a nostalgical observations that when I met Professor Soundararajan for the first time, that is probably somewhere in 1987, 1988, when he was in high school, and till 2 years to finish the high school, he had already one paper published, and that paper was actually the elementary proof for the partition, the asymptotic formula for the partition. And now it looks like that we have come a full circle.
Well, uh, I do recall that, Balu, but this was one of my worst papers probably at that time, and it was in math student. And of course, at that time, actually, I should say that when I first met Balu, and I was in high school in seventh grade, and at that time I was just playing around, and I had no idea of asymptotics. And since Balu is nostalgic, I can also say that at that time I just had a calculator, and I could look at P of 200, and I could take the 200th root of P of 200 and say, oh, it goes to some constant. And I came to Balu and said, well, maybe there's some constant number bigger than 1, which these guys tend to. And then he was patiently explaining to me that if I have something that grows like e to the square root of n, and I take nth roots of that, then it just goes to 1. And so I learned basic asymptotic theory from Balu all that time, all that while back, and a lot of it has stuck. And of course, I'm most grateful to him for all the time that he spent with me at that stage.
Good. Thank you. Thank you very much for giving this lecture, even with your busy schedule. And very good. Then I'll probably write you a letter about the other things. Oh.
Great. Thanks, everyone. Bye. I hope you have a very productive rest of the week.